So yeah, let's talk about these. Okay, first one. How are we going to do that one? You can't. You're right. How come?
It's the sum of squares.
Okay, it's the sum of squares. Good, because we don't have any patterns for fourths, right? But we do have sums and differences of cubes. Whenever you see a two-term polynomial that you're supposed to factor, or where you're solving a polynomial equation, what are you always going to look for? What really are the only options? Sum of squares, difference of squares, sum of cubes, difference of cubes. That's it, right? Those are really your only options. Okay, so that one doesn't work. So it's done. It would just be, we're going to get imaginary solutions. We're only looking for real solutions, let's say. Okay? How about the next one? Okay, we're going to factor by grouping. What do we always want to try to do first, regardless of how many terms there are? See if there's a greatest common factor. Is there?
No.
There is not. Okay, so we can just move on. So we'll factor by grouping. And let me make this a little bigger. How about? Okay, what's that going to look like? Divide it up, right? So I got my first two terms, second two terms. How do I do that? Okay, take an x cubed, that'd be my greatest common factor from the first group. And then we're left with what? Okay, so now you can kind of, when you're doing factoring by grouping, then I've got to have something common between the first and second groups, right? If it's going to work. Is there any way, so I'm going to show you maybe just a little, we're going to take this one step further than we did last time. And this is kind of maybe even further than the book goes in a way, but it's a better strategy. I mean, if you can do this very logically. We have to have one of those two things in common if factoring by grouping is going to work. Obviously, we couldn't pull out an x cubed from the second group, right? It's almost always going to be the leftover factor. 99.9 times it's going to be the leftover factor. And so what we could do is we could just assume that we're going to get the same leftover factor and see if we can make that work, right? So we could just say x minus 5, and then the question is, can we make it work? Can we factor something out so that we end up with a leftover factor of x minus 5? Negative 64. Okay, so then we've got this plus, and then we're going to factor out a negative 64, and that does work, doesn't it? Because 5 times 64, negative 5 times negative 64 is 320. Everybody see that? Okay. What's really the only option in a case like that for the greatest common factor of the second term, or second group? Really, did everybody see that our only choice would have been that, wouldn't it? If we have to have a leftover factor that's just an x minus 5, then in order to get an x there, we would have had to factor out a negative 64. So this boils down to just, does that work? Is negative 64 times negative 5 320? And it is. You see that? You guys see how we can make that? We don't even have to think that hard about it. And so then, now where are we? So this did work. How do we finish this up then? So we got two groups, two terms. The common factor of the two groups is x minus 5, and then we're left with x cubed plus negative 64 is just x cubed minus 64. Okay? And now what?
Oh. Math scared me.
Okay, now what? if we were, and with you guys, we can kind of be a little more sophisticated with this. If we're just looking for real solutions, we could, skip ahead. We haven't learned this yet, but what are we gonna get from what's the zero of our first factor gonna be? 5, for sure, right? Done. The question is, do we need to keep factoring, right? Because really, remember, the purpose of factoring is only to break this thing down far enough that we can use the zero product property and get all our solutions, right? There's no reason for us to factor unnecessarily, right, if we're trying to solve an equation. So, do we need to factor this or not? Okay, it's kind of an iffy one. The answer is, maybe yes, maybe no, depending on how far we need to go. Now, if we're just looking for real solutions, the answer is no. We don't really have to. Because, and let me remind you about something we talked about last week, but I want to revisit this. So this gives us, if I use the zero product property, right, I'm just setting each factor equal to 0 and solving, right? You good with that?
Yeah.
Okay, so if I just set this factor equal to 0, this appears to be analogous to the problems that we did in Module 3, right, where we had a quadratic equation where I could point to a single x and isolate it, right? What would be the steps I would need to isolate x in this problem? Add 64, right? And then take a cube root of both sides. Okay, so then we get x equals, do I have to put a plus or minus?
No.
I don't, because it's an odd root, right? So I get plus or minus, I don't get plus or minus, I just get 4. Okay, and that's right. Those are my 2 real solutions. Okay, but I just want to plant this seed. We're going to talk more about this in the future, but could there be some other non-real solutions? Yeah, there could. In fact, I just want to tell you something. Hold that thought. You asked a question?
Yeah.
Okay, one sec. So we're going to talk about in the future, but I'm going to go ahead and spring this on you now. If I have a polynomial equation of degree 3, how many complex solutions do you think we're going to get? We're always going to get 3. We're always going to get as many solutions as the degree of the polynomial every time. Now, it's possible that it could be like a double solution. It could have a multiplicity of 2 or bigger, and then it counts for multiple solutions. For example, if I said something like x squared equals, or let's even make it like x to the 4th. If I said x to the 4th equals 0, then what's my solution? I mean, plus or minus 0 is just 0, right? So I would get, it seems like I've got one solution, but it's got a multiplicity of 4 in that case, right? So it counts as 4 solutions, and why is that significant? The only thing I can tell you right now why that's significant is, remember when we were sketching polynomial functions, you tell me if this is my polynomial graph, what can you tell me about that x-intercept compared to that one? What was the difference between those types of x-intercepts, where it cut directly through? So it crossed right through. What does that tell you about that factor? It's not taken to any power. It's got a multiplicity of 1, is what we'll soon say. We haven't said those words yet, but that's kind of remember we talked sort of about that, right? We said it wouldn't be squared. What about this one? Okay, this is taken to a power, right? Now, we haven't talked about this yet either, and we'll come back and revisit all this, but I just want you guys kind of, maybe just in your head, just kind of thinking about how, putting this together a little bit. What power do you think that would be? Could be squared. What else could it maybe be? Okay, it could be any even power, because it bounced like an even function, right? So it could be x to the 4th, it could be x to the 6th, it could be x to the 10th, right? What if, though, it did something a little different? What if it did something like this? There we go. What if it looked almost the same, but instead it did something like that, where it still didn't cut directly through, but it was tangential, right? But then it went down. It eventually did go through.
Means it's odd power.
Okay, that means it's gonna have a multiplicity that's odd, right? Does that make sense? Because it looks like, if you just look in isolation at this intercept, it looks like an odd function, doesn't it? Right? And so it would have an odd multiplicity, 3, 5, 7, etc. Okay? I mean, that's really kind of college level stuff, but you guys are, I mean, for you, I want you kind of thinking along those lines, because you'll come back to this time and time again, even, later on in future classes. If you have some insight into that, it just makes it a lot easier, right? So how does that relate to this problem? Well, we said that this had one real root, right? It has to have a total of 3 complex solutions, though, right? And so maybe it's just that's an x that's got a multiplicity of 3, right? Possibly, but maybe not. What would have happened if we would have factored this? What would we have gotten? Yeah, that's a difference of cubes, right? That looks like x cubed minus what cubed? 4 cubed. Okay, so we could replace the 64 with a 4 cubed, right? And so then we can go back. I'm just going to get rid of all this stuff now. Oh, jeez. It's already been one of those days. All right, so there we go. All right. Okay, so we could have said, we could have broken this down into x. What's the pattern going to be for x minus, or for a minus b cubed? I'm going to get a minus b times a squared plus ab, right, which would have been 4x, plus b squared, which is 16, right? And that's all equal to 0. So then we get our other, and that one should have been, right, everybody see that one should have been down there too? But we just already wrote a 0 for it. Everybody get it? So then here, this one would have given us a 0 of 4, which we got already, right? But what about this guy over here? Okay, right, because we said, remember we already talked about when we use those sum or difference of cubes, factoring patterns, we get a linear factor that gives us a real 0, but then we always get an irreducible quadratic, right? The quadratic one's never going to yield real zeros. We already said that. But, I forgot your question. Yeah.
Oh, for stuff like the first one we did x to the fourth, something 16. Why don't you just isolate x from that?
We can't. Yeah, we can't. I mean, but on the one that we did here, I could isolate x. You're right, but I'm not going to get any real solutions, right? Okay, and we'll go back to that. We're all done. Let's take one quick look at that. But if I set this equal to 0, I do have a quadratic equation, right? And so I am going to get some solutions. They just may not be real. So what if we did that? What if we applied the 0 product property and actually set this one equal to 0? Well, we could just use the quadratic formula, right? And we get x equals negative b, so what's that? Negative 4 plus or minus the square root of b squared minus 4 times a times c divided by 2, right? And so then that's going to give us negative 4 plus or minus the square root of 16 minus 48. So what's that, 32? Negative 32? No yawning. Over 2 equals negative 4 plus or minus, what's 16 going to break down to? The square root of negative 30. I'm sorry, I already kind of gave it away. Square root of negative 32. What's that going to break down to? So we're going to get 6. That's going to be 16 times 2, right? That's our biggest perfect square, right? We've got a negative there, so that's giving us an I. Yes?
Isn't 16 times 4 64?
Oh, I'm sorry. You're right. Yeah, you're right. So that should be 48, shouldn't it? My mistake. Everybody see that? 4 times 16, 64 minus 16, so that should be 48. Let me change that. So it's still going to give us the greatest common factor of 16, which is going to be times 3. So what's that going to give us then? We're going to get a plus or minus the square root of 16 times 3, but then I'm going to have an I there, right? All over 2. And so I could break this apart, which I always need to do with a complex solution anyway, right? Make it in the form A plus BI. And so we end up with our final answer, the imaginary parts being negative 2 plus or minus 2 radical 3i. Okay, so then here's the other bomb I want to drop on you here. When you always are going to get, and this is the fundamental theorem of algebra is what this is going to be called when we talk about it. We always get the number of complex solutions corresponding to the degree of the polynomial. But when we got these imaginary roots, we got them from the quadratic formula, right? Now let's think about how this is all consistent with the stuff we said about the discriminant. I just love how this stuff all comes together. When we evaluate the discriminant, there were 3 possible outcomes, right? And let's kind of go back and look at those. If the discriminant, and remember what that means, that's just the part under the radical, right? If the discriminant is positive, what do we say always happens? 2 discrete real solutions, right? If the discriminant was 0, what did we say? Okay, we said 1, but we're going to have to amend that just a little bit, aren't we? Because really it's 1 double solution. So it actually, as far as the fundamental theorem of algebra counts, it really counts as 2, doesn't it? Right, and we just looked a second ago at the example like where we said x to the 4th equals 0, and we got x equals 0, right? Well, if I looked at the discriminant of this, if I broke this down into 2 quadratics, I'm going to end up getting 0 for both of those, right? So this, it looks like 1 solution, but as we said, it really counts as 4, right? Same kind of thing with if the discriminant in a quadratic were 0, looks like 1, counts as 2 though, actually. But what happens if it's negative? We got 2 complex solutions with imaginary parts. Do you see that it would be impossible to ever get 1? It's impossible to ever get 1 because of this. There's a plus or minus in the quadratic formula. The only way I can get imaginary parts in my solutions is if there's something under the radical. It's negative. So I'm going to get a plus and a minus part of my answer, right? So that implies something really significant. It implies that if we get complex solutions with imaginary parts, they always come in pairs. You could never have, for example, and I'm jumping the gun on this a little bit, but it just is important to have a little insight. I firmly believe that. If I had some kind of a polynomial, like, I'm just going to give you one like this. We're not going to do this, but what if I gave you x to the 5th minus 4x to the 4th plus 3x cubed minus 2x plus 1? What's the degree of that polynomial? How many complex solutions does it have to have? 5. Okay, what are the possible natures of the outcomes? Could I have 5 real solutions? I could. Could I have 4 real solutions? No, you can't. How come? Okay, say it louder. I'd only have one complex solution with an imaginary part, and that can't happen. They have to come in pairs. So what's the next highest number of real solutions I could have? Be 3. I could have 3 real and 1 complex, right? Could I have? So I couldn't have 2, right? I couldn't have 2 real because that'd leave me with 3 complex, and that doesn't work. They have to come in pairs, right? So the only possible numbers of real solutions would be 5, 3, or 1, which tells us that it'd be impossible for me to have no real solutions. But that should be right, shouldn't it? Based on the end behavior, it's an odd function. And so the end behavior is going to be opposite, right? So we know it's going to go up to positive infinity on one end and down on the other. It could be switched, right? But there's no way it could not go through the x-axis. It's got to go through at least once, right? Isn't it cool how it all just kind of comes together? What about, question? So what if I had a 6th degree, I thought I heard something. What if I have a 6th degree polynomial? How many real solutions could that have? Okay. Couldn't have 5 though, right? Could have 4. Could have 2. or it could even have
0.
0, which makes sense because the end behavior is going to be, either up on both sides or down on both sides. And so if it was a fourth degree, it could do something like that, right? And never touch the x-axis. Agreed? Okay. One other thing, maybe we can go further with this, which actually makes things even easier. Look at the nature of these solutions. How could we describe, if I break those into two separate, let me take a picture of this. So if I write those as two separate solutions, I want you to tell me what the relationship is. I either get x equals negative 2 plus 2 radical 3i, or x equals negative 2 minus 2 radical 3i. What do you notice about those two solutions? How would you describe them? They're kind of like cousins. What's the... Stands found. Okay, so our dog. So what would you call that relationship? They're kind of like cousin solutions. They're not inverse. What's the word we use for? The only thing different is conjugates. Yeah, they are conjugates, and the fact that they have i's in them means that they're complex conjugates, right? So this is a complex conjugate pair, right? So complex solutions to any polynomial equation always come not only in pairs, they come in complex conjugate pairs every time. Later on in the year, I'm going to show you guys some ways to look at that are really cool. If you look at that like in the complex plane, it makes sense that it has to be that way. I won't do that now. That's too much extra stuff. But this gives you a little more insight, right? Okay, so let's try another one of these then. Just going to throw some of these at you and we'll just talk about the solutions. Okay, how about something like that? Okay, good. So everybody take a second, and before you answer anything, just in your notes, just kind of think about this, come up with some ideas. Question, Kirk?
So when you're factoring it out on the previous ones, you have to put it into the quadratic.
Like on the last one?
Yeah.
Okay, so yeah, getting back to practical question on that last one, Kirk's asking, he's getting down to business here and asking, so do we have to factor it out to here, right? So yes and no. You want to be efficient about this. What if the question said find all real solutions to the equation? Would we have to actually factor it all the way then? We wouldn't, right? Then it would be easiest for us just to do it this way, just to set this blue factor right here equal to 0 and solve. But if the question said find all solutions, complex solutions, real and imaginary parts, then we would have had to have factored that. Okay? Yep.
How do we put this in
Well, okay, so let's look at the question and see. This one came from there. And this one just said completely factor the polynomial and write the polynomial in factored form. So we're just going to write it as a completely factored quotient or a product of all the factors. Okay. I don't like questions like this as much as the ones where they say solve the equation, right? But this assignment is going to say all the questions are going to say completely factor. So it's kind of like overkill on factoring just to drill it in and get you some practice. But then I'm going to come back with one more assignment from this. This is a huge, in my opinion, this is a huge section that doesn't get covered enough in books. And so I'm going to go back with one more where you're actually solving equations. And then you can bail out of the factoring whenever it's most convenient, right? Okay. All right, so thoughts? What can we do with that? I heard a good suggestion. We always want to do what first? Greatest common factor. So we could factor out a 4x squared, right? So if we factor out a 4x squared, then what are we left with? X to the fourth plus 24x squared. 34. Whoops.
Whoa.
That's terrible. I gotta go back. Plus. Okay, good. So that helps, right? We got a blue monomial factor out front. What's going to be if this were an equation in standard form, z equal to 0, what's going to be the solution of the blue factor? It's going to give us what 0? X equals, if this were z equal to 0, what's the solution that comes from this one? When does 4x squared equal 0? X equals 0, right? If it's a monomial factor like that, where it's just some number times, some coefficient times x to any power, what's the 0 always going to be? 0, yeah, every time. Okay, what about the red one though? That's weird, right? It's a quartic polynomial, fourth degree polynomial, so it's not something that just fits neatly into any, there is no quartic equation, right? It's got 3 terms. Now let's think about what we can do with 3 terms. Think about our history with solving polynomials. 2 terms easy, right? It's going to be a sum or difference pattern. That's it, the only possibility, right? If it were 4 terms, the ones we just did, we'd have to group it, right? But what did we always do? The only experience we've ever had with a 3-term polynomial has been a quadratic trinomial, right? So we have to ask ourselves then, could this be written as some form of quadratic trinomial, right? Could we write this? Is it possible to take this red factor and write it as something squared plus some coefficient times something to the first power plus something? Yeah, x squared, right? We could say, and listen to this statement very carefully, we would say that the red factor is quadratic in x squared, meaning that if we break it into pieces of x squared instead of x, it does look quadratic, doesn't it? Right? So it looks like x squared plus 34, whoops, that's supposed to be an x squared. X squared plus 34x squared. Hang on. I know this doesn't seem like it's important. I didn't mean to get this right, but I want to color code this so it kind of, you see the pattern better. Plus 225, right? If those x squareds were x's instead, that's easy, right? You either factor it or do what? Quadratic formula, right? Everybody see that? So now, same exact approach, only instead of x equals, we're getting x squared equals, right? Well, let's see, are there numbers that multiply to 225 and add to 34? I bet there are. Probably, what is that going to be? 25 and 9? Yeah, right? Multiply to 225 and add to 34. So there are magic numbers. So we could break this up into x squared and x squared, and then the magic numbers would be plus 25 and plus 9, right? Everybody see that? Okay. Well, just because, I mean, just think of factors of 225 that add to 34.
Oh, yeah.
So, right, so 25 times 9 equals 225 and adds to 34, right? And so then, could we go any further with this?
Let's not.
Okay, only if we were trying to find, only if we were trying to find imaginary numbers. And if we're factoring, we're stuck. There is no factoring pattern for x squared plus 25, right? If we were solving an equation, we could set these equal to 0 and get imaginary solutions, right? But if we're factoring this thing, that's a roadblock. We can't go any further because sum of squares pattern doesn't exist, right? Last thing, how much time we got?
2 minutes.
Okay, that's fine, that's all I need. So what if we didn't see those magic numbers? I just want to show you that the quadratic formula is going to give us the same answer. If we didn't see the magic numbers, we could have just skipped down here and factored this by using the quadratic formula. How do you do that? The quadratic formula doesn't give you factors, it gives you zeros, right? Well, let's just see if we can cheat a little bit, because you can. When you're factoring, you can always cheat with the quadratic formula. What if we had set this up, pretend it was equal to 0, right? If that were equal to 0, what would we have gotten? The quadratic formula would have been, instead of x equals, it would have been x squared equals, right? X squared equals negative b plus or minus square root, oh my gosh, b squared. What's 34 squared? Somebody quick, tell me, calculators.
1,156.
1,156 minus 4 times a, which is 1, times b, which is 225, all divided by 2, right? And so if we kept going with that, we'd get negative 34 plus or minus the square root of 1156 minus 900. So that's just going to be 256, right? Square root of 256, which is 16. So we get negative 34 plus or minus 16 over 2. Well, look at, what if we take the plus sign? Yeah, we'd get negative 34. Anyway, okay. We'll wrap this one up at the start of class tomorrow. Okay, I got an assignment up. Go.